algebraic equations, the equations of the type fx equal to 0. So, we want to find the values of x that are going to satisfy the equation fx equal to 0. We have looked at several methods, bracketing methods and open methods to solve the problem of fx equal to 0, and of these methods that we have looked at, we have specifically considered the fixed point iteration, the Newton-Raphson method and the bisection method to look at their stability and convergence properties. So, that is what we have essentially done so far. We have specifically focused on problems in single variable. What is actually going to be also important is look at problems in multivariables. So, just to motivate the problem in multivariable, this is what we had looked at when in the first lecture of that module, of this module. So, extension to multiple variables. So, let us say we have, instead of a single variable x, we have n variables x1, x2 and so on up to xn, and these variables satisfy set of equations which is f1 of x1, x2 and so on up to xn equal to 0, f2 of x1, x2 up to xn equal to 0 and so on until fn of x1, x2 up to xn equal to 0. Okay. So, these are the n equations in n unknowns, and the shorthand notation for writing all this is f bar of x bar equal to 0 bar. Okay, so oftentimes we will just write this as f of x equal to 0, and based on the context we will figure out that this is actually a single variable or a multivariable case, but what x bar means is nothing but x1, x2 up to xn, just the same notation that we had used earlier in our linear systems part of the course. So, x bar is nothing but x1, x2 up to xn, and f bar is nothing but f1 as the first element, f2 as the second element and so on up to fn as the nth element in this particular equation. Okay. So, what we are interested in doing is to extend the numerical methods that we have talked about to problems of this sort, of trying to get x1 up to xn, which are solutions to f of x bar equal to 0. Okay. So, that is our aim in today's lecture, and the two methods that we are going to look at is the fixed point iteration and the Newton-Raphson method. So, let us look at the extension of fixed point iteration method. Okay, and the extension of fixed point iteration in this case, what we are going to write is write the equations. We are going to write the equations in the form of x1 bar x1 of x1 is going to be equal to g1 of x bar, x2 equal to g2 of x bar and so on up to xn equal to gn of x bar. Okay. And as we had seen in one of the previous lectures, how we can convert f of x equal to 0 in this form, there isn't a unique way in order to convert f of x into this form. One very straightforward and not necessarily the best way, but one straightforward way of writing g bar is we can write the equation to the equation f of x bar equal to 0, we can add x bar on either sides, and we can write x bar is going to be equal to x bar plus f bar of x bar, and this we can call as our g bar of x bar. Okay. So, this is one straightforward or simple or naive way of converting fx equal to 0, to convert fx equal to 0 to the form x equal to g of x. So this is one straightforward way of doing this, and once we do this, we will essentially get x1 equal to g1, x2 equal to g2, and so on up to xn equal to gn. This is what we are going to get, and let us recall what we did essentially in Jacobi iteration, and that's pretty much what we are going to do in fixed point iteration in multiple variables. What we will do is, let us say we will start off with initial guess x11, x21 and so on up to xn1. These are going to be our initial guesses. Okay, which we can, in the shorthand notation, we can write this down as nothing but x bar of 1. Okay, so we will start off with the initial guesses x11, x21 up to xn1, and then we will use the fixed point iteration in order to get I plus 1th value from given the ith value. And the shorthand notation, it's a very straightforward way of writing in shorthand notation, and that's going to be x bar of I plus 1 is going to be equal to g of x bar I. Okay, what this essentially means is it essentially means is x1 I plus 1 is going to be equal to g1 of xi, x2 I plus 1 is going to be equal to g2, and so on up to xn I plus 1 equal to gn of xi. Okay, and this is what we really mean by this particular expression. Now the question is, when do we stop and when do we say that the particular equations have converged? So the third item in our algorithm is to check for convergence. Okay, and in this particular case we are going to define our error EI, we are going to define is E, or rather we should say EI plus 1, keeping in touch with what we were doing in earlier lectures. EI plus 1 is going to be defined for each variable. It will be defined for x1, x2 and so on up to xn. So in general, EI plus 1j will be defined as the difference xj I plus 1 minus xj I, the absolute value of this. This is going to be our ej I plus 1, and the objective is that, so for example we have x1, x2 up to xn, we want to ensure that the largest amongst these error values is going to be less than certain tolerance, and that is what we are going to write this down, is we will write down maximum over j of ej I plus 1 should be less than or equal to E tolerance. Okay, and this is the criterion that we are going to look at. For example, if the true solution in two variables, if the true solution is 1 and 1, and let us say that x5, so this is the true solution x bar, and let us say at certain point x5 turns out to be 1 and 1.05, then the error in this particular case is 0, the error in this particular case is 0.05, and the max, when we run max over the errors over here, the max value is indeed 0.05, which is not going to be less than our tolerance value of say 10 to the power minus 4, and if that is the case, we are going to keep running these iterations over and over again until we reach the desired convergence levels. Okay, so this is what we will get. So if until this particular condition is satisfied, the fixed point iterations are going to be repeated over and over again. Okay, now let's consider the convergence criterion for the fixed point iteration. what we had done for with fixed point iteration in the previous lecture is that we had found that the error E I plus 1 was going to be equal to g dash of zeta multiplied by EI, where zeta was some point that lied between xi and xi plus 1. Okay, or yeah, it need not, I mean the signs might possibly be reverse as well if xi is greater than xi plus 1. So zeta is a point that lies between xi and xi plus 1. Okay, so this is the expression that we essentially got for a single variable case, and this came out right out of the new excuse me, this came right out of writing or expanding the Taylor series expansion and throwing away the terms in the second order and higher orders in the Taylor series. Keep in mind that the Taylor series expansion in multivariable case is going to look like, so g of x bar is going to be equal to g of xi, or let us say g1 is going to be equal to g1 of xi plus partial g1 with partial x1 computed at x bar I multiplied by x1 minus x1I plus partial g1 with respect to x2 computed at x bar I multiplied by x2 minus x2I, and so on up to the nth order term, and then we will have the second derivative terms and so on. Okay, keep in mind that for a single variable this is the same as g dash of zeta. So if we were to extend this particular error analysis to something in n variables, so instead of having just g dash of zeta multiplied by EI, we will have essentially dg by dx1 plus dg by dx2 plus dg by dx3 and so on and so forth, and so those are the terms we are going to get. So just an extension of this particular expression to an n variables case, and you can look up any of the standard textbooks such as the ones given in the overall syllabus for this particular lecture series. You can so there's Chhapra and Canal, numerical methods by Chhapra and Canal, numerical methods for engineers by S.K. Gupta, or you can look at basically numerical recipes in C by Press et al. So any of these standard books, if you go and refer to them, some of the derivations for what we are doing, more detailed derivations will be provided by them. I am not going to run through the details, but essentially what you will get is EI, the error at I plus 1th iteration in the jth variable is going to be equal to, so we will have this g dash terms for g1 with for gj with respect to each of the variables. So we will have partial gj by partial x1 multiplied by ei1 plus partial gj by partial x2 multiplied by ei2, and so on up to partial gj divided by partial xn multiplied by ein. Okay, so this is the error in the I plus 1th iteration for the jth variable, and what we need to do essentially is to find out the maximum of those errors and see how that maximum error compares to epsilon tolerance, and without actually getting going through the derivations, what I will write is I will write the final result for that will guarantee the tolerance, and the final result some of you might immediately be able to see the final result with respect to a single variable case was just dg by dx was the absolute value of that would be less than 1. That was the sufficient conditions to guarantee stability. Now the sufficient condition to guarantee stability is going to be sum of all these guys. The sum of all these guys should be less than or equal to 1. So I will write down the conditions for stability. Okay, for the fixed point iteration, the sufficient condition for stability is going to be dgj by dx1 plus dgj by dx2 and so on up to dgj by dxn computed at x bar of I should be less than or equal to 1, okay, for all j equal to 1 to n. Okay. So, what that means is partial g1 by partial x1 plus partial g1 by partial x2 and so on up to partial gn by partial g1 by partial xn, that should be less than 1, and the same would be true for partial g2 by x1, g2 by x2 plus g2 by xn, that also should be less than 1 and up to for all the n functions. Okay. So, that is essentially the sufficient conditions for sufficient condition for stability of the fixed point iteration. Now, one of the comments about this particular sufficient conditions for stability of fixed point iteration is this is a fairly stringent condition for a general function, a general set of functions gi to be met, and it is not always possible in a general nonlinear set of equations for this conditions to be met. That actually is something that will limit the applicability of the fixed point iteration. Of course, the first problem is that the overall fixed point iteration method is linearly convergent, as we have seen over here, is that the error ei plus 1 is proportional to error ei to the power 1. It is a linearly convergent system and it remains linearly convergent when you have essentially multiple variable case also. The overall convergence of this system is not guaranteed for a large number of problems of our interest. One of the things that we had done earlier in order to convert a general expression to the form f of x bar was if when we to the form x equal to g of x. So, let us say we started with f of x equal to 0. What we had done essentially in this particular case is we had added x bar onto either side of this equation. We can actually do a slight modification to that. If f of x equal to 0 is the problem that we want to solve, we can multiply this equation by beta. If f of x, if the solution for f of x equal to 0, we need the solution for beta multiplied by f of x equal to 0 is also going to be the same solution, and then on both sides we can add plus x. Okay. So, what we will get essentially is an equation of this particular form, and this becomes our g. Okay. So, x equal to x plus beta times f of x is going to be our g, and we can then judiciously select our beta such that the sufficient condition for convergence is satisfied. It's possible to do that. Sometimes the beta that you will need is going to be a very small value beta, and if that is the case, the moves that will be made by a fixed point iteration method are going to be very conservative moves. That means we are going to move very slowly towards the solution. Of course, when we have this as our g of x, what we will get is g dash of x is going to be nothing but 1 plus beta times f dash of x. So we want our f dash of x to be negative in order for this to work. If f dash of x is going to be positive, we can take a negative value of beta. So we can appropriately choose that value of beta such that the sufficiency of this of the condition dg by dx less than or equal to 0 is satisfied. Not that fixed point iterations are not applicable, it's just that the applicability range of the fixed point iteration methods often in practical chemical engineering problems, at least in my experience, has been fairly limited. So that is about the fixed point iteration. We now go on to the workhorse, which is essentially the Newton-Raphson method, and we will look at the extension of Newton-Raphson's method to a multivariable case. Okay, so now we are going to look at the Newton-Raphson's method for a multivariable case. So we have f1 of x bar equal to 0, f2 of x bar equal to 0, and so on. So let us consider any jth function fj of x bar equal to 0, and and currently we have the current guess of x bar, current guess is x bar at I. Okay, so what we are going to do is we are going to linearize fj of x bar around x bar I, and that we can write down and as fj of x bar is going to be approximately equal to fj of x bar I plus we will have dfj by dx1 multiplied by x1 minus x1i plus dfj by dx2 multiplied by x2 minus x2i, and of course this is evaluated at x bar I and so on up to dfj by dxn evaluated at x bar of I multiplied by xn ith iteration, sorry, multiplied by xn minus xn at ith iteration plus higher order terms. Okay, so this is what we get. If we neglect the higher order terms, we will get this particular expression as approximately equal to the right hand side. Now what we had done in deriving the Newton-Raphson's method is we had put this particular guy equal to 0, and whatever solution that we get was x of I plus 1. That is what we had done. So this is essentially, this amounts to looking at keeping only the linear terms in the expression. When we essentially do that, we will take, so we have put this guy equal to 0, we will take the fj on to the left hand side, and when we do that, we can, in the matrix notation, we will be able to write this particular equation as negative of fj computed at the ith value is going to be equal to dfj by dx1 dfj by dx2 and so on up to dfj by dxn. These are all evaluated at x bar I, the ith guessed value of x bar, multiplied by x1 minus x1i, x2 minus x2i, and so on up to xn minus xni. Okay. So this is what we are going to get for fj. We'll get this for f1, we'll get this for f2, we'll get this for f3 and so on, we'll get it for all of the n functions. Okay. So what we can do is, then when we stack this particular things together, what we will get so to simplify this a little bit, what I will do is I will just go over for a 2 variable case, so just f1 and f2, and then we can see what happens in 2 variable case, and we will be able to extend it to n variable case. In the 2 variable case, we will have f1 of x1 comma x2 is going to be equal to dou f1 by dou x1 minus x1I plus dou f1 by dou x2 minus x2I. Okay. And this we can also write it as dou f1 by dou x1 and dou f2 by dou f1 by dou x2, this multiplied by x1 minus x1I and x2 minus x2I. Okay, that is going to be minus f1 of x1 comma x2, or rather minus f1 of x1I comma x2I. I missed the I subscripts over here. Likewise, we will be able to write this for f2 as well, and for f2 this will end up being f2 computed at x1I and x2I is going to be equal to partial f2 by partial x1 partial f2 by partial x2 multiplied by, and again I am just going to be a little bit lazy and use a shorthand notation over here, and I will call this as dx1 and dx2. Okay. So these are going to be 2 equations which we can then combine together to write this as minus f1 and f2, and again I am being lazy and writing the shorthand notation over here, is going to be equal to partial f1 by partial x1 partial f1 by partial x2. Okay, these two guys will be on the first row, and on the second row we will have partial f2 by partial x1 and partial f2 by partial x2 multiplied by delta x1 and delta x2 multiplied by value of delta x1 and delta x2 that solve this linear equation are nothing but the difference between the I plus 1th value of x and ith value of x. Okay. So we will invert this particular matrix, so we will represent this as J multiplied by delta x bar is going to be equal to f bar computed at x bar I. Okay. So our delta x is going to be nothing but J inverse f, that is going to be what our delta x is. So our delta x bar is going to be equal to minus J computed at x bar of I inverse multiplied by f bar computed at x bar of I. Okay. This is essentially what we will get. If I go back to an expression over here, I made a slight error in this, I missed out the negative sign over here. So this negative sign has to be there. What we have done is taken J inverse and multiplied it over here, and if you notice this is essentially equivalent to the problem that we had solved in module 3. The problem was b equal to ax, and we wanted to find the solution to the linear equation b equal to ax. So in order to find this delta x bar, you can use any of those methods such as Gauss elimination or Gauss Seidel method or any of those methods in order to get delta x bar equal to negative of j inverse multiplied by f. And remember, the delta x what we had was nothing but x I plus 1 minus x bar at I. Okay, again these are vectorial notations, which basically means it does matter whether you pre multiply or post multiply j. This is a pre multiplication by j inverse. Okay, so what we will get eventually is x bar of I plus 1 is going to be nothing but x bar of I minus j inverse computed at x bar of I multiplied by f bar computed at x bar of I. Okay, for an n by n system, j inverse or j is going to be nothing but partial f1 by partial x1, partial f1 by partial x2, and so on up to partial f1 by partial xn. Like the second row will be partial f2 by partial x1, partial f2 by partial x2, and so on up to partial f1 f2 by partial xn, and we will continue that to partial fn by partial x1, partial fn by partial x2 up to partial fn by partial xn. This computed at x1i, x2i, and so on up to xni. This is going to be our matrix J. Our f is nothing but f1 computed at x bar of I, f2 computed at x bar of I, so on and so forth, and this is going to be our multivariable Newton-Raphson's equation. Again to recap, we have df1, df1, df1 on the first row, df2, df2, df2 on the second row, and so on up to dfn, dfn, dfn on the nth row of the Jacobian matrix. Okay, so that's essentially what we get with respect to the Newton-Raphson's method. The convergence or the order of convergence for the Newton-Raphson's method is going to be quadratic order, and that's really because what we have done with the Taylor series expansion is that we have retained the Taylor series up to the first derivative term, and we have discarded the second derivative term, and the term that is discarded, the leading term that gets discarded, has an error which depends on square of that term, and that's the reason why the Newton-Raphson's method has a quadratic convergence rate. Okay, so this was essentially the extension of fixed point iteration and the Newton-Raphson's method to multivariable systems. So extension or improvements to Newton-Raphson's method is what I am going to consider next. Okay, and what we will do is we will start with a single variable case. I am not going to go through the derivations. What I want to give you a flavor of is that there are several improvements to the Newton-Raphson's method that we have come up with in the last 80 to 100 years, and those improvements, to look at those improvements, you can go and use various sources, and one of very good sources to start off with is numerical recipes in C or Fortran. That's the name of the textbook. Okay, this is a textbook that you can refer. It's a very good resource for all numerical techniques, and it is available on the website nr.com. So you can go to the website nr.com and take a look at the numerical recipes textbook. Of course, the numerical recipes textbook is not free, freely available on the website. I believe it's something like $19 or something like that to download the latest copy of the numerical recipes textbook. The earlier versions, the second edition of numerical recipes textbook, I believe are available for free to download. So you can go to nr.com and download essentially second edition, and I believe that is numerical recipes and Fortran. That's the second edition that is available for download from nr.com, and it's a very good resource if you want to understand or use numerical recipes in a better way. Likewise, if you want to just use some of the numerical techniques, then there is another website called netlib.org. This is an online repository of a lot of numerical codes that including linear algebra, nonlinear equation solving, ODE solving, and so on, that is available freely for downloading. You can go to netlib.org and choose an appropriate solver if you are going to use any kind of complicated problems that you intend to solve. The objective of this particular lectures is to give you an overview of or an introduction to the numerical methods, to computational techniques, so that you can get the confidence to go and look at some of the more advanced methods that are being used. Okay, so anyway, the improvements to the Newton-Raphson's method, there are several ways in which people have figured out how to improve the Newton-Raphson method, and all of them are for looking for particular set of problems. One of the improvements that was done by Ralston essentially is for, let's say we have f of x versus x, and if we plot say f of x, and let's arbitrarily, this is the kind of curve that f of x we get, where f of x is going to intersect the x axis at multiple points. Now we know that Newton-Raphson's method, starting from an initial guess which is close enough to the solution, converges very quickly to the solution. There is a second order convergence to any of the solutions. However, if a Newton-Raphson's method is going to be used in order to find the multiple solutions to the equation fx equal to 0, it fares quite poorly. It does not converge as quickly as one would like. So what researchers figured out in 1970s, late 1970s, essentially is that we have the equation xi plus 1 equal to xi minus fi divided by f dash I. Okay, this is a typical Newton-Raphson's method. What we can do, a slight modification to this particular method could be to multiply this with some factor m, and the question is what is the factor m that we choose, and Ralston essentially came up with this m should be the number of solutions that you get, the number of times that this particular curve intersects the x axis. So in this particular case, the m that I am going to use is going to be 4 in order to get the fourth solution to fx equal to 0, and by using this particular method they have found that by choosing m equal to 1 they will be able to get the first solution very quickly. In order to go to the second solution, you choose a different value of m in order to improve the convergence rate. The problem with choosing this m is, in general, when we are given a general f of x, we do not know a priori how many times this f of x is going to intersect the x axis, and if that information is not known a priori, we may not really be able to use m equal to 4 for example in this particular case, if we do not know that 4 roots of this particular equation exist. Okay, so that is one issue with this particular method. But what the same researchers realized is that if the solution to f of x equal to 0 and the solution to f of x divided by f dash of x equal to 0, these two functions have the same solutions. Okay, it can be numerically be proved that the function f of x divided by f dash of x has the same solution as the function f of x equal to 0. So what these guys did is, instead of using this particular way of solving things, they defined a new function, let us call h of x. They defined h of x as nothing but is defined as f of x divided by f dash of x. Okay, this is going to be our h of x, and now the objective, instead of finding the solution of f of x, the objective is now changed to find the solution of h of x, and that's becomes our new problem. So what we can have is x of I plus 1 is going to be equal to x of I minus h of x of I divided by h dash of x of I. Okay, and this is going to have for the function h of x, this will have the same convergence properties as the Newton-Raphson's method, but in order to get the solution of f of x, this will have a faster rate of convergence than the original Newton-Raphson's method, which was essentially xi plus 1 equal to xi minus h of x of I. Okay, so what we can then do is we can expand this h prime as nothing but f prime squared minus f multiplied by f double prime divided by f prime squared. That is what we will get over here, and h is nothing but f divided by f prime, and we can rearrange and we can get this overall expression. And if you are interested in knowing, you can look at this particular method in any of the standard textbooks that follow. So we'll just look at what this particular expression by using this would mean. Our h dash, as I said, is going to be f dash multiplied by f dash, which is f dash squared, minus f multiplied by f double dash divided by f dash squared. Okay, this is what our h dash is going to be. So h divided by h dash is so h by h dash is going to be nothing but f by f dash divided by f dash squared minus f double dash, and this whole thing divided by f dash squared. So you take f dash squared over here, so to the numerator, and you will get f dash, and one of the f dashes will get cancelled. So this will get cancelled along with this, and then when you take f dash on to the numerator, you will essentially get f dash. Okay, so this is going to be our h divided by h dash. So using that equation, and if you haven't followed the derivation, what I suggest you can do is take a piece of pen and paper and rederive it yourself more slowly. But what we can get is xi plus 1 equal to xi minus fi f prime I divided by f prime I squared minus fi and f double prime I, okay, and this is going to be our improved Newton-Raphson method. Okay. Let us define our function f of x as equal to f square of x. Okay. So, we have just squared this particular function. Now, f of x, because it is just square, is going to always be positive except when x is the solution to f of x equal to 0. When f of x is going to be equal to 0, our capital F x is going to also be equal to 0. For all other values of f of x, our capital F x is going to be positive. So, for example, for a general function of this sort, if this is f versus x, our f capital F versus x is going to be something like this, where this and this are the same values. So, if we call this as the solution x bar, this is going to be the same as x bar. So, x bar is the minima So, x bar is the minima of f, which is defined as going to be equal to f square, and we can use essentially this property in order to get an improvement in the Newton-Raphson's method. And the improvement in Newton-Raphson's method using this particular property has gotten to do with the first and second derivatives of this function f of x. This is a little bit more advanced for the sake of our course. I am just mentioning it so that some of you who are interested in learning the Newton-Raphson's method can then go ahead and look at some of the more advanced versions of the Newton-Raphson's method. And again, the first place where you can start off with is the numerical recipes by Press et al. That book would be a good source to start off with going into more advanced topics in the nonlinear equation solving. Okay, and one of the more straightforward ways of getting around, and this is basically using this result. What the result that I am going to show next is something that comes out of this particular result itself. Is for a multivariable case, what we had said was, what we had derived is xi plus 1 was equal to xi minus j inverse f computed at the value I. Okay, so this is what we had derived, and this derivation worked extremely well when, as long as J was non-singular. That means as long as the rank of the matrix J was equal to n, this particular case worked really well. However, if the rank of the matrix J is not going to be equal to L, then we need a slight modification to this. Keep in mind that this, again I am using pedagogical liberties over here, I am not using mathematically correct terms over here, but this we can actually write this as J transpose J inverse multiplied by J transpose. Okay, as long as the rank of the matrix J is going to be positive, as long as rank of matrix J is going to be equal to n, this particular guy is going to reduce to nothing but J inverse. Okay, but this is where a small trick comes in, is instead of writing it in this particular form, we write it as follows. We will write this as J transpose J plus beta times I inverse J transpose. Okay, so what we have done is we have introduced a small perturbation parameter beta over here, so that whenever this J transpose J starts getting close to being singular, we can use an appropriate beta value to give that small perturbation in the slope. So what happens when J transpose J is singular, or when f dash is 0, is we reach a maxima of this sort, and this is where basically the tangent line is parallel to the x axis. So what this does is, in the multivariable case, it gives a slight slope, and by giving it a slight slope we will prevent the overall method from stopping when J is not going to be invertible. Okay, so that is the whole idea over here, and the expression remaining terms remain the same as we had in the original version of Newton-Raphson's, and that term, that is going to be xi plus 1 is going to be equal to xi minus J transpose J plus beta I inverse of that multiplied by J transpose multiplied by multiplied by f of xi. Okay, and this is basically called the Leuenberger-Marquardt method of solving nonlinear equations. Okay, so we end our this particular lecture over here. What we have covered in this lecture is essentially multivariable extension for fixed point iteration. We saw that the fixed point iteration had a linear rate of convergence for multivariable system. We also saw the stringent conditions for the sufficient conditions for stability of the fixed point iteration. Then we went over to multivariable case of Newton-Raphson's method, and in the last 10 or 15 minutes I gave a very brief and a very superficial, I may add, introduction to the extensions that we can have to Newton-Raphson's method, the Ralston's extension and the Leuenberger-Marquardt extension. The idea behind covering these extensions is for people who want to read further in order to get more information about this. You can now go ahead and read some of the literature and perhaps try to make sense of it. Okay, thank you very much.